idea theme, which is kernel regression, which is a non-parametric regression. So far what we are doing is a proper statistical derivation of regressions, parametric regressions. But there is enough thought and enough work that went in building non-parametric regressions. We'll look at kernel regression. Then I want to get to logistic regression, which is, of course, a major second class of generalized linear model. Probably the popular version of alternative of linear regression for classification. Logistic regression is a misnomer. They call it regression, but it's actually classification. The only reason why they call it regression is because you get a probability between 0 and 1, any number. You know, your y is not truly a 0 or 1, but a probability. But still, it should have been called logistic classification, but then world decided to call it that. And towards the end, I will discuss panel regression, which because quite a few have shown interest. So that's the theme for today's session. So, again, let's start with what is maximum likelihood estimator. It's a very simple concept. All it says is, you have given me some data and I have to build a model. And that model has some parameters. They typically represent it with theta. Parameters, for example, a linear regression, y is equal to theta naught plus theta on x. The parameters are theta naught and theta on. Anything you can think of a set of parameters. Now, in a normal distribution, for example, the parameters are the mean and variance. Once I define mu and sigma square, my normal distribution can be plotted. I can plot the other end of that is I can plot various normal distributions with various values of mu and sigma square. I can plot various lines with various theta naught, theta one. Maximum likelihood estimate is the simplest of the assumptions that the theta naught and theta one are the mu and sigma square that I need to use for this distribution is the one that maximizes the probability of the data. So, if this is my data, the histogram is my data, I could have gotten any of these normal distributions and many more of these normal distributions. I could have gotten. Of all these, I think this one or this one, whichever, this one has the highest likelihood, maximum likelihood to be the right model, simply because it explains the observed data better. So of all the possible models, the model that explains the observed data better is the model that you should choose. I mean, that's a very, very intuitive, simple thing. There's nothing great about it, but it works out to be a very powerful and robust framework. Given a data, pick the model that gives the best fit. This one obviously has a lot of advantages. It makes a lot of intuitive sense. But please note that this estimator is biased by observations. Particularly if it is biased towards high likely observations. So if I have an event that has only 5% chance of occurring, if I take 50 or 60 observations, there is a very high likelihood that I may not see it. I may not see that 5% event. Then my maximum likelihood estimator will actually build a model that is biased towards the more frequent 95% event. Right? If there is a, let's say if there is a 1% chance that an event occurs, I have taken 50 observations. There's a very high likelihood that all 50 are the 99% chance event. If I take 100,000 observations, yes, I'll get 1,000 of likely that I'll get many of the low likely event. But even in reasonably sized observations, I will get bias towards the majority event. In such a case, my maximum likelihood will build a model that is biased towards the more frequent event. That's the problem. And then, you know, we have already talked a lot about Bayesian, where we said, no, I will assign a prior probability. So this is only what the likelihood says. Now there is something else my prior says. My real final thing is the combination of those two. In your regression, as we are going to see, maximum likelihood is the least squares estimate. Prior probability is your regularization, lasso or ridge. A combination of these two is what you finally build as your model. So but maximum likelihood by far has been the workhorse. Maximum likelihood followed by gradient descent was machine learners' workhorse. Any model that you develop, we'll see for at least two models, linear logistic. We use maximum likelihood estimator, build a likelihood function which I want to maximize, or a cost function which I want to minimize. And then I'll take it. Then I'll use gradient descent to minimize that. Right? So now, how do I actually find the maximum likelihood? The idea is very simple. The likelihood L is theta values for a given data. X here is the data. Yeah. X here is the data. Theta is the parameter. So remember, in likelihood estimator, what is the variable? The thetas are the variable. It's a bit unusual. We are born and we are grown to believe that X is the variable. But when I am doing likelihood estimator, I am figuring out which model. Is this line the best fit? Is this line the best fit? Is this line the best fit? Or is this line the best fit? The variables between these lines are not the given data. The M and C, M1 C1, M2 C2, M3 C3, M4 C4. So I have to differentiate with respect to the M and C, or theta naught and theta 1, not with respect to X. Is that clear? Right. So the likelihood of a theta set for a given data set is very simple. The probability of finding the first data point in that data set times the probability of in all statistics, I make an assumption that the samples that I have chosen are IIDs. IID is identically, independently distributed. Even when the samples are independent, probability of finding all those samples, joint probability, P of sample 1 intersection sample 2 intersection sample 3 intersection sample 4, joint probability is nothing but probability of the first sample times probability of second sample times probability of third sample. We studied that. There's no conditionality there. They're all independent. So all I am saying here is the probability or likelihood function theta is defined as probability of seeing the first point times probability of seeing the second point times probability of seeing the third point as a function of the thetas. Now I express this in terms of theta. My entire effort is expressing these probabilities in terms of theta. Then I need to find that theta for which this probability is highest. So I have probability multiplier of probabilities, all expressed in terms of theta. What theta values does it take a maximum? And how do I do that? Basic calculus or gradient descent. Why, some function is expressed as a function of theta. At what theta value it is highest? Dou f by dou theta. If I have multiple thetas, I equate it to 0 and then compute the values of theta. And I do dou square f by dou theta square. If I don't know whether I am maximizing or minimizing, and find the values where it is 0. If it is positive, that's a minimum. If it's negative, regular calculus. Where I cannot do calculus, we already looked at gradient descent, where I randomly start, subtract a dou theta by dou x, dou f by dou theta, and then I keep updating my value. That's it. That's the workhorse. Typically, people find that this is a bit more complicated to handle, so they actually take a logarithm on both sides. So they don't maximize likelihood, they maximize log likelihood, which is okay. Logarithm is a continuous, monotonic, increasing function. Logarithm never goes non-linear. So if I am maximizing a logarithm, I am maximizing the function itself. The maximum value of log fx and maximum value of fx are same because logarithm doesn't disturb that. It's just a mathematical convenience. Most of these functions, as you can see, have lots of powers in it. P1x times P2x times P3x times P4x. So I have whatever theta to the power of n it gets. Logarithm just makes it n log theta. That's the only advantage. So it's mathematical convenience, nothing significant. Right, so that's it actually. Now, in linear regression, the idea is this is what my hypothesis is. Y is equal to okay. Technically, if I was not traveling as much as I was traveling in the past week, I should have typed this, but I cut them from multiple places, so I have an apology. In page to page, at some point you see alpha, some point you see theta, and some point you see, and again I didn't take it from any one book because I wanted to get the simplest possible explanation. So I will give enough disclaimers, but please bear with me for those notation changes from here to there. So this is alpha beta, here is theta naught theta 1. But this is what we learned, there's nothing, this is the random error. What did our generalized linear model, 3 assumptions that we said? This is independent of any x1, x2. It only depends on that, it's a normal distribution across the space, normal or any distribution, with same mean and same variance across the space. Okay, throughout. So that is a random variable, this is the error component. And this one is my, these are the parameters. In linear regression, I expect my function to be just a unity. It could be any other function. It could be, e to the power of minus in a generalized linear model. It could be, y could be any smooth continuous function of x. It happens so that in linear regression, I just assume that it's a unity, that function. Right. This is my linear regression. My epsilon is, mean is 0 and some sigma squared, some variance. Now, first point has some epsilon value. What is its probability? Likelihood of probability of first point is 1 over root 2 pi sigma square exponential minus epsilon 1 square by 2 sigma square. This is for the first point. I go for the second point. Go for the third point. N points. That's my likelihood, right? I just multiply for a given sigma square and mu is 0. I'm assuming on the line mu is 0. I can standardize anything. So for a given sigma square and 0 mean, my normal distribution of the probability of individual points are this, and hence my likelihood is a multiplication of this. So these get multiplied n times if there are n points, and these get added. E to the power of m1, m2, m3 is equal to e to the power of m1 into e to the power of m2 into e to the power of m3 e to the power of m1 plus m2 plus m3.
For all the points when you assume the mean will be 0.
Yeah, please. Yes, I just assume, actually I don't have to, just to simplify. If there is a mu also, it doesn't change in anything. But I can always subtract, as long as the mean and variance are same, I can always subtract the mean and divide by variance, and I can make it 0 and 1. So it doesn't really hurt in any way. The assumption that I made is mean is same for all. That is the more important thing.
Do we also, when we say homoscedastic for
No.
error, do we also mean that error at point 4 is independent of error at point 3?
Exactly, and it is same. So I am saying my epsilon at x1 is independent of epsilon at x2. In fact, epsilon at x1 is independent of x1. Epsilon at x2 is independent of x2. x1, x2 don't determine. So while this part of the equation is determined by the independent attributes, this is a random variable. At a given x1, once I get the mean distribution, the y can fall anywhere around it with a probability. That probability is independent of where I am measuring. Throughout the system in homoscedasticity, it is the same. That's what I mean. So it is not that at x1, the mean of the variance is 1 and x2, the variance is 100. Which means the variance is a function of x1. That is heteroscedasticity. And you can see if I assume heteroscedasticity, this equation doesn't fall here. It is 2 by sigma 1 square times sigma 2 square, sigma 3 square, sigma 4 square, exponential 1 by 2 sigma 1 square, sigma 2 square, sigma 3 square. It becomes your linear, your least square will not work. That is why it is an important assumption. Unless you assume that the variance is independent of x1, you cannot get from MLE to least square. Right. That's it actually. Now epsilon I is equal to y minus alpha bxi. I just substitute here. 1 over root 2 pi sigma square and exponential minus 1 over 2 sigma square yi minus alpha bxi whole square. You can now see already markings of least square regression, least square error. From here, is this step fine? I just substituted. Actually, it cannot be not fine. Epsilon I is equal to y minus alpha bx. Now, then my regular process. I want to do dou L by dou alpha, dou L by dou beta. But before that, it's a lot more easy, as I mentioned, if I take a logarithm, log likelihood. Because this guy, I can avoid completely that exponential guy. So when I take logarithm of that, it's just 1 over the root 2 pi n becomes n by 2 ln 2 pi. Sigma square n becomes n by 2 ln sigma square minus 1 over 2 sigma square. I get rid of this exponential completely. So this is m times n times p. Ln of m times n times p is ln m plus ln n plus ln p. So I get ln m plus ln n plus ln p. That's it. Now this is my likelihood. So there are two things I can do. And this is a choice, some derivations people, it's your convenience. I either can maximize my likelihood or I define these are constants here. Well, this is not a constant, but for a given sigma, when I do dou ln by dou sigma, actually this is a constant here. These are what I am really interested in. What is the alpha beta? This is a constant actually, what am I saying? Sigma is a constant anyway. Alpha and beta is what I want to find out. So I am interested in this part of the expression. So there are two options for me. Find the alpha beta that maximize this, or because there is a negative sign, find what minimizes this. I call this error function. So you either maximize your likelihood or you define an error and minimize that error. And in this case, that error is nothing but this, which is your least squares regression, least squares estimator. So as long as alpha and beta are linear, as long as sigma square is constant, you can see least square estimator coming in. Whether whatever is the distribution, actually, if it's normal distribution only, I get least square. Thinking about it.
Because the function will be
Yeah, the function will not be in a Poisson, it will be a different function, right? In something else, it's a different
I
function.
think we are not assuming that the mean is 0 because when we are writing yi minus alpha, by default we are subtracting the point from the mean. So alpha plus beta xi is the mean expected value at that point.
Ah.
And yi minus that is by default we are accounting for the mean in the last step.
Yi minus alpha.
So E1, E2 are the
Yeah.
residuals.
Ah.
So there is no need of any assumption of mean being 0 at any point.
Yeah. You're right. I'm seeing that. Yeah, because I'm anyway subtracting that. I don't really have to. Yeah. Yes. You're right. So if it is some other distribution, obviously I need to redo the process. And as I will show in logistic regression, least squares won't work. I need to rewrite the equation. But the process is very simple in any of the statistics. As if you really ever want to get into mathematics of it, start with the maximum likelihood estimator, compute the likelihood, which is nothing but the probability based on your assumptions, multiplication of the probability, the joint probability of seeing all the data under that distribution. Express it in terms of the terms. And then what theta maximizes that. You do it for log likelihood and not just likelihood. That's a mathematical convenience. So in linear regression, I have this as my hypothesis. And based on that, I assume this is normally distributed. And now I write the joint probability distribution of each and every point, multiply that, and I get my likelihood. And I do my log likelihood, which is nothing but this plus this. Log of this plus log of exponential this thing. Log of exponential gets cancelled and I get this. So now I either maximize this or minimize this. So least squares is nothing but a straight outcome of your maximum likelihood estimate. And the assumption that your error is normally distributed across the space. For whatever it is worth, now you know. So what is more important here? If the derivation is not particularly appealing to you, leave it. Don't worry. But this is only half the problem solved, right? Now actually I need to find where it is minimum. Now I need to apply gradient descent. But it's not as scary. If you think about it, you can, if I don't do the absolute analytical model, what is my gradient descent? Dou by dou alpha, which is people, to make things easy, divide this with 1 by 2m, just to make things easy. So that's fine, 1 by 2m, m is the size of the data, positive, 2 is anyway positive. Maximizing, minimizing doesn't hurt if I divide with 1 by 2m. So what is then dou by dou alpha? 2 by 2m times this thing, into dou by dou alpha of this is 0 anyway, minus 1, right? Dou by dou beta, which is, by the way, to make that easy, people actually do it alpha x naught plus beta xi, make x naught 1, make x naught 1. But that's only because the equation looks consistent. But if I do 2 by 2m times this times minus 1, that is my dou by dou alpha. Dou by dou beta is 2 by 2m times this times beta. Sorry, times xi. I am differentiating with respect to alpha beta times xi. I got dou by dou alpha, dou by dou beta. My gradient descent is, sorry, nothing, I didn't make any mistake. There is in gradient descent there is a factor. If you remember, there is another alpha. What is my gradient descent? Just to get you, theta naught is equal to theta naught minus alpha times dou L by dou alpha. Dou L by dou theta. Theta 1 is equal to theta 1 minus alpha by dou L by dou theta. This is my gradient descent, right? We agreed on that. So I just take a derivative, randomly, empirically choose one alpha value, subtract that from my initial random value, and then I update and I keep searching till I hit. That's it. Now, I apologize for the terms that I use, but this alpha is different from this alpha. This alpha is the parameter. You call it theta naught or m or something. Dou L by dou m, which is a nice thing you got. 1 over 2m into 2, and a simple function. Dou L by dou c, another simple function. That's it. If you have multivariate regression, you have 10 such equations for 10 attributes. And you just empirically, randomly initiated theta naught and then keep upgrading your value till it converges. So technically, if you really want to get nerdish and geekish, you can code it from the ground up. Alright, if you ever plan to get into a PhD program in machine learning or statistics, this will be your homework number 2. Right? They ask you to manually code the linear regression. And by the way, equations get a bit tougher, but neural network can be coded like this. It's just that engineers are a bit more lazy, so we don't code things, we use whatever is available. Okay, but you can do this. There's nothing unusual. In fact, the most tricky thing is this alpha. The only reason why I asked you not to code it is this you can code. But in gradient descent, people have already done 100 PhDs. So where do I start my theta naught theta 1? They actually take eigenvectors of the original space. Can I randomly start at any theta naught theta 1? You can prove that by selecting theta naught theta 1 initializations intelligently, you can reduce the step size from exponential to logarithmic. And people have done PhDs in this. You don't have to invent everything from ground up for yourself, right? So there are libraries available, so do some of those things. But concept is this, but there's a lot of growth happened, so it's better off we just have to. Any questions on the underlying mathematics? I'll again hit you hard with logistic regression. Anyway, I have, we'll do that also mathematically. But for linear regression, are you comfortable? Jagan, this definitely is not to be asked in GNQ. Okay? Yeah. Okay. Good. So we did. This is the traditional linear regression. But now think about it. Let's get lazy. What is the simple way to build a linear regression? I mean, oh man, this is maximum likelihood and normal distribution and all that is too many nice things to complicate.
Choose alpha and beta so that you minimize.
Choose alpha and beta.
So that you minimize the error from your.
How do I do that? That's not an easy task. Genetic algorithm or something I have to use. No, I didn't mean. Well, is that feasible? Can I randomly choose an alpha beta to make it? That will be a random search, right?
Random search, but then.
It's not an easy
then
task.
iteratively update it. It's like.
And iterate it, but it's your gradient descent. But then you're not doing the first 10 steps, but you're doing what they are doing. The other idea, weird it may sound, is KNN regression. All I'm saying is you ask me what is the value of y at x1, x2, x3. Some x1, it's a 3-dimensional system. What is x1, x2, x3? Now I look at my existing data, identify 5 nearest points around x1, x2, x3. There's one coordinate where you want a y value. And can I not use a k nearest neighbor? So all I am saying is, you have given me points like this. This is my data. So now you want a y value here, right? I will take average y's of these 4. Just mean of those 4 y's. Does that work? It's actually not bad. This is called KNN regression. I mean, why can't we do it? Just when you want to find a y, look at the 4 nearest points. All you need to define is what you mean by near. And in most problems of your type, Euclidean distance is a good enough metric, or Manhattan at most, if that makes sense. So you take the 4 or 5 or 10, empirically you figure out what is giving the best thing, divide some data as train and some as test, and build with 2 nearest neighbors, 3 nearest neighbors, 4 nearest, 5 nearest, just take averages, see which one has given the least mean square error, and use that as a.
But this will be used at points where you don't have the data. Whereas
Regression can be extrapolated. That's true. That is true. But if I have large enough data, well, I will still use it. It will be incorrect. If you want me to find data here, there will be 4 nearest points to that. I'll just do it. But yes, there is a problem there. We'll address that. But we'll address as best as we can. That is the negative. What is the positive here?
it's not constrained by the linear criteria.
It's not constrained. No assumptions. Normal, nothing. I'm not making any assumptions. And more importantly, am I building a linear in a line regression? No. I can actually now get a arbitrarily shaped regression. So that is the beauty. I am not even restricting myself with an hypothesis. Forget about assumptions. That's the beauty of non-parametric.
That's not useful, right?
That's not useful.
I mean, or in this case, unless you.
If prediction is what you are interested in, I see that if explicability is what you are interested in, this is not useful. But if your goal is prediction, isn't this a reasonable idea?
We are not taking into account the nearest neighbor, right?
Yes.
Basically, we are not taking into account the whole thing.
Good.
So
Yeah.
we are in a way sort of fooling, like, not fooling, but.
So is localized regression, that is the nature of k nearest neighbor. As I said, there is a whole lot of scientists who believe I should not take a global view when I am making a prediction. Just take a local view and make a prediction. Now, how local is my view? I will empirically determine. So is that necessarily a bad assumption? Does mind build models? So the question that people ask is, this is intelligence. Does one class of people, the statisticians and pattern recognizers, say mind actually builds models? You say somewhere in your brain someone is sitting there and doing his least squares and maximum likelihood estimators and coming up with models. There is this other class that says no, mind doesn't have that much of smartness. All it is God has given us a humongous storage space. So I keep storing anything that I see. The moment you show me anything, I identify the nearest things to that in this data, and based on that I decide what I want to do.
But even in linear regression, we don't.
Huh? Linear takes global view, right?
No, but it's also affected by the points in the vicinity.
Yeah, but not just but it is affected by all of them. That's what. But what I am saying is I will not even think, and more importantly, the point that the linear and this one is model building. What I am saying is linear regression is I am looking at the data and I am coming back with, after differentiating and everything, y is equal to m1x plus c. What these guys say is there is nothing like that. While mind, then you get rid of the data. Once you have y is equal to m1x plus c, you get rid of the data. You have only that equation in your mind. So pattern is believe our brain has multiple models. The similarity guys on the other hand said no, that is nonsense. We don't have any model. I have data. Now you give me a point, I will identify the nearest points to that and I will react based on that. I will just take an average of that. So I can never get rid of data. If I have amnesia, my mind is doesn't have any learning. Because my mind doesn't have any, amnesia only with respect to data, let us say. Let's say I have equations coming. So no, they said no, not like that. Your brain doesn't work. So we don't know which one is the right model. Anyway, it's a controversial thing. I don't want to get in, but I want you to understand the difference between these two. In one, I have made some assumptions, built some global minimization factor. So I am not taking a local minimization. I am saying, you know what? My likelihood is that theta, which on average reduces the, maximizes the probability or minimizes the error of all points across the system. That's my, yeah.
But sir, when we take the class variables, we sort of still take a very pseudo-localized approach in regression as well, right? If I try to build a model and I don't fit one single line, but I say there are 3 different values of slopes and intercepts.
In your panel regression kind of a thing, right? That is three regressions, but still it's a variant of the regression only.
Right.
The moment you are building a model, you are taking more than one point into account.
Yeah, but then again, we are not taking a super globalized approach.
That's okay. That's still you are building a model, right? Yeah, that's where I draw the line. But in the parametric also there is, if you think about it, there is a small model there. I take the 5 nearest guys. Okay, what you are saying, and which is right, is can I build a KNN regression where for any given point I will identify 5 nearest points and build a regression just based on them? Now that's an ultra local regression. You can do that. Now that's a combo of parametric, non-parametric. There is non-parametricity because I only took that 5. Then there is parametric thing because I actually built a least square regression on top of it. People do that.
Can we call that curve fitting?
Yeah, spline fittings, they call cubic splines and all the splines. They are localized regressions. In fact, people call it localized regressions, right? The ultimate of that is no model. Just take those 5 points and take an average. 3 points, take an average. Right?
Isn't it like more of a overfitting linear regression?
Yeah, overfitting is a good thought. You know, the whole idea here is if there are outliers in the data, this is a bad model. But if that oddly behaving one is truly a data point. So I see all 20, 10, 20, 10 and suddenly a 300. Now nearest neighbor approach actually is influenced by the fact that there is a 300 here. My linear regression doesn't, because I'm building a global model. It will say this is an outlier. My Cook's distance will be very high, I drop it. But in reality, let's say that is truly a real value. Then local regression is the only way to actually predict in and around that the value will be high. So if it's outlier, it's a danger. If it's truly a nonlinear function with spikes, actually this is better. So that's why you need to understand the data, trade-off, and see how well you are doing on the test, etc. So it has the advantage that it captures the local behavior very well. It has the disadvantage that it gets influenced by local behavior a lot. Is that a positive or a negative depends on the problem at hand. And so again, there is no free lunch theorem in machine learning. No model is better than other models all the time. That's the theoretical computer science theorem called no free lunch theorem. You know, you can prove that. By the way, if you think this is weird what we are doing, you should see the work of theoretical computer science. Oh man, the probably approximately correct theory. You know, most of our GMQs they fall in that, right? Probably approximately correct. So, there is a whole framework based on which people derive some fascinating things. You know, what is the maximum data that you need to solve a problem? What is the minimum data? What is the maximum error bound? Some wonderful things, probably approximately correct, PAC framework. So what I say is, so you ask me, hey, build a model. I say I'll build a model. Then you say, hey, how accurate will you get it? What is my immediate as a data scientist? Depends on how much data you give me. You give me more data, that'll be more accurate. Okay, so when will you be 100% accurate? Truly as a mathematician, what I'll say, give me infinite data. So I know you can't do that, so you can never ask me for 100% accuracy. Great. So I have to, for accuracy, I'll have to come up with definitely a 1 over n function. N is infinity, then only my error. Error is proportional to 1 over n. When n is infinity, my error is 0. Right? So good. So I'll get one equation. Now, okay, with this equation, I will give you 100,000 man. So your equation says 94% accuracy. If I give 100,000 records, will you stay on that? Is it written on wall that you will give me 94% accuracy? Then I said, oh, no, wait. I am 95% confident that I'll get 94% accuracy. Right? So that is called, so there are two things. The solution I give is approximate unless you give me infinite data points. That is the approximate part. Now, whatever I promise, I am only that much confident. That is my probability. So probably is, I am 95% confident that I will get 98% accuracy given 100,000 records. So that is the framework on which a lot of theoretical computer science is built. It's a fascinating theory, but I mean, it's difficult to get grants in that, nobody cares for it. But it's interesting. There is a group of scientists who just sit and solve these theoretical problems. It's wonderful. I actually don't find it as ridiculous as probably it is. It's not bad actually. Anyway, On the other hand, this is the laziest way of solving the problem, right? You just take average of 10 guys around it. Now, however, I'm not going to talk much about it, but I just want to introduce you to something. Then I'll move to the non-parametric version of this. This is called radial basis function regression. So, what did we say? Oops. Oh. Why did I do this? Sometimes this happens, you know. So, linear regression, as we learned, is sigma I is equal to 1 to n wi xi. So far, that's what we have been solving. W1 x1 plus W2 x2 plus W3. But there is nothing when I am hypothesizing, as long as I keep these linear, there's nothing that stops me from having any function here. Right? That's what we learned. Generalized linear model, I will have a different function. Radial basis function is one such linear regression where I assume my y is a linear sum of some Gaussian bell curves. Are you guys familiar with the Fourier series? Right? What are they? At some level, what is it? Fourier series is nothing but however complicated your overall function may be, you can express it as a sum of sine waves. All you need is to give a different amplitude and different phase. If I identify the right amplitude, any complicated function can be written as a sum of sine functions or cos functions. Does that make sense? Any function, obviously you can, sine is a nice thing, and you can just multiple sine waves of different amplitudes, you can get a nice functional description. Taylor, any function can be written as sum of polynomial functions. If you extend this idea, cannot any function be written as a sum of exponential functions? Sum of bell curves. All I am saying is, can I not, my y is this. Can I now write it as sum of I will use a different amplitude and different wavelength. Is that fine? Yes or no? And I do see a stunned silence, but is it weird, or the advantage is, again, I don't have to be linear. I don't have to hypothesize that it's a linear function, but because my coefficients are linear, it still is a linear regression. Because my x's, I never cared about them, right? It's linear regression, which means I can use, if I assume my errors are normal, I can actually use least square. It is just that my y minus xi is a much more complicated thing, but I'll get an error square term that I want to minimize. There are a few caveats. It has to be a continuous, differentiable kind of a thing. If the functions get discontinuous at some places, it gets discontinuous means they go to infinity. Then your rates get messed up. But if you actually have those things taken here, a continuous differentiable functions with different weights, you can express it as an infinite sum of those functions. Yeah. Yes?
Or is it that exponential is a special case of trigonometry, where every trigonometry can be expressed as exponential?
But Taylor, on the other hand, proved that exponential is a special case of polynomial also. So is a trigonometry. So any polynomial, any exponential, any sinusoid, all are in the same family, which makes it any continuous differentiable function technically, theoretically can be written as a polynomial sum, and hence it is a manifestation. So you can do that. So as long as those caveats are met, then this is a big, this is an aha moment. This is one of the greatest, simplest ways to solve any problem. All I need is a complicated function I don't even have to understand, as long as I know that I can write it as a sum of some simple functions. Well, yeah, we are weird that we call these simple functions, but they are simple actually. As I'm going to show, exponential is a beautifully simple function.
All this, where you express it as the sum of simple functions. By default, you need to know the function to express this in the form of simple. Fourier series, you can't write.
That's where I use my maximum likelihood. So given this data, so what I'm saying is I have observed some data. Why? Okay. Yesterday, actually, not yesterday, a few days back, my daughter asked me this question. She's in 8th grade, so I asked her, I was teaching her functions. So I gave her x1, x2, x3, and I gave her compute y is equal to 2x squared plus 3x minus 6, and compute y. So she actually she computed all y's. Then she came and asked me, okay, if you give me x1, x2, x3, I am computing y. But how will I compute f if you give me x1, x2, x3 and y? I was shocked. I said, oh, that's what I am teaching for the past 5 years. There's no single way to do that. So, right? I said, wait for some more time. I don't understand it well enough to teach it well enough to an 8th grader. But the point is, what is your challenge in supervised learning? You are given x1, x2, x3. You are given a y. Now you have to step back and figure out what is the damn thing that's connecting those two. The problem is, it is not an invertible function. There can be a million different ways in which that f can be formed. And then you used Occam's razor. You said, I will use the simplest possible explanation of the lot. Because recently, one of my mentors gave a wonderful example of Occam's razor. So let's say, 2 guys come late to the class. Did I take this example in the last class? 2 guys come late to the class. So I asked the first guy, why did you come late? I think I took this example last time. No? So the first guy said, man, you were so boring last time. What are the chances you will get really interesting today in the first 10 minutes? So I came late. The second guy said, no, Dr. Murthy, you are wonderful. And I really tried to get up very early in the morning. But, someone called me from some place at 6:30 and this ICICI credit card guy, and he would never put it down. And then I get up, my cook had a flu, so he couldn't do the breakfast. And then, the cab driver who comes on time every day got delayed by 10 minutes. And I was so upset, I didn't even feel like taking bath. I came running and I took an auto rickshaw and came, and suddenly there is this train gate that fell, And with all that, because of my sincerity, I came only 10 minutes late. Who should I trust? First year, right? There are just too many improbable events happening. Right. So that is Occam's razor. Occam's razor at some level is, you can build multiple explanations to the same thing. Take the one that has least number of improbable events. You use that in machine learning, right? For a given x and y, I can build it as a sum of linear functions. I can build it as a sum of sinusoidal functions. I can build it as a sum of radial basis functions. I can build it as anything, neural networks. And the idea is, of all the things, what is the simple is what I believe is the right fx. But that's an Occam's razor. Maybe it is the complicated one that is right. Maybe the second guy was actually right. Maybe, at least I would like to believe so. Right. Yeah.
But suppose when we take normal linear, suppose we take the function as it is.
But you don't know the function. What are you taking as it is? You have some y's and you have some x's.
Yes, but then if I am writing it as a sum of some sign, and intentionally adding at some level some complexity and as well as some little bit of periodicity. I cannot say.
No, you don't. That is not a worry. The moment you play with amplitudes and period and the widths, what he said is any non-periodic function can be expressed as an infinite sum of sinusoidal waves.
But why would I want to do that?
Why would you want to do that if the function is extremely real in signal processing? If those of you who studied signals, can be really complicated. Linear assumption is bad there. So the best you can do is Fourier. Again, why would I want to do it? Yes, you are absolutely right. Why am I expressing it as an exponential or a sine or a linear function? The single biggest advantage in all three of them is their differentiations are simple. If I express it as sine, it becomes cos. If I express it as e power x, it is e power x. If I express it as x, it is a constant. That's my, our polynomial is easy enough to do. X to the power of n becomes nx to the power of n minus 1, though it is not actually as elegant as. If I have a choice between a polynomial and exponential, I'll actually go for exponential, simply because the calculus part is easy. That gradient descent part is easy. That's the only reason. Otherwise, it is, yeah, good question. I mean, are you crazy, man? Why are you trying to express it as a sum of multiple bell curves? Simply because God just had a wicked sense of humor and made the derivative of e power x. And so we can't come out of it. I mean, it's a loop. Right? Yeah. Beautiful nagging lady. You just live with it. And e power x and that's it. Yeah. So, right? Anyway, the nagging man also. Handsome, yeah. You live with them. Right. Now, having said that, so there is, though by the way, this is not my favorite, but I have seen recently that many engineering applications, like I was working, I told you, with respect to Chrysler, we did a very nice project actually. The project is approximating the approximate. So when you make a car, people don't make a physical prototype of the car to see how the noise is, how the fuel efficiency is, things. They use something called finite element model. Now this finite element model is essentially, now any of these engineering behavior like noise, vibration, temperature can all be expressed as a partial differential equation. But the space on which you have to differentiate is so complex that you can't manually solve it. So what engineers do is they divide the space into small regions. And on each region, which is a square or a triangle, your partial differential equation is very easy to solve. All you then ensure is two boundaries, the boundary points, actually the approximation I do here, approximation I do here matches. That's all. So keep solving these partial differential equation on small square regions, ensuring that at boundaries they just match. You just put a scalar factor. So I get an approximate function. This is like the workhorse of engineering design. Every place where you are designing an automobile or anything to do with it, people actually, instead of making a prototype in real life, they create a computational geometry and run a finite element model. Right? Now, what Chrysler came to us is, they said, this finite element model is taking 8 hours to solve in a supercomputer, because you are designing a car, right? So it's like you divided it into million elements and you are solving million partial differential equations and combining. So it's a pretty intensive work. And the second bigger challenge that they had is there is no functional form. So once I build the entire equation for x1 is equal to steel, the material is steel, temperature is 20 degrees. A steel means it has iron and carbon in a particular percentage, nickel and cobalt and all those things. Now I want to see how it works if I change the temperature to 21 degrees. Because there is no functional form, I have to rerun the 8-hour analysis. That's it, there's no functional form. So they said, these are all the results of my finite element model. Can you now build a data science model on my finite element model and come up with a functional form for my finite element prediction? So essentially I will give you x1, x2, x3, my inputs, and the output of my finite element. I'll give you 100 such analysis. Now I have a simple regression problem. Can you actually tell me what will be my y for a different set of x1, x2, x3? And then when I did literature survey, people extensively use this form because that is a non-linear thing. And people actually write it as a regression with which is a linear sum of radial basis functions. I was actually surprised that this is used. Till then, I thought it's only a theoretical application, the theoretical thing, I can write it as a sum, but I never used it. For the first time I saw that whole literature where the people actually express y as a linear sum of radial basis functions of x. Because my y in that case is highly non-linear. My hypothesis that it's linear is a very bad thing. But then I said, why should I do it? I will use a neural net, which is data science has a much better way of solving this problem. You know, non-linearity, we don't have to do this. We do support vector machines, neural networks. We have other ways of doing. We remember this. Only in other engineering disciplines, non-linearity is expressed as a linear sum of non-linear functions. That's what I am doing here. A sum of Fourier series, a sum of this thing. But on day one I showed you, we have a much more elegant way to do non-linearity. One of the most elegant ways of doing non-linearity is support vector machines, where anything that is non-linear in lower dimension becomes linear in higher dimension. So we just multiply it, it becomes linear, build a regression there, project it back. And that happens to be an elegant way to do non-linearity. Neural net is a fairly elegant way to do non-linearity. Random forest, which we will learn, is another extremely interesting way to do non-linearity. So as a field, we are much more, much better suited to do non-linearity than these days. This is a very naive way of doing non-linearity. Instead of taking x1, take a complex function of x1 and then add. This is generalized linear model, you know, at some level. Anyway, now that you understand how to incorporate this non-linearity, after the break, I will actually talk about a more interesting non-parametric variant of this thing. So my goal is, you saw KNN regression, where I said, hey, I want to predict something, I just take 5 guys around it and take an average. But as you pointed out, the problem with that is, if I am far away, okay, I am not getting, which is okay, I can live with that. But more importantly, as someone else pointed out, it's way too local, man. You are not taking the impact of any farther away points. Technically, I should take, ideally, what is the right answer? Based optimal classifier, the value here should have W1 X1 for the nearest point where W is very high weight, and somewhere far away, very low weight. But still it should impact. Why I should only take 5 points? I should take the entire data and put the higher weights to nearby data and lower weights to far away data. And that regression is what I want to introduce you to, which is called kernel regression, which is based on this radial basis function, but it is not a global thing like this. It's a non-parametric regression. But the idea is extremely simple. If you want to predict a point, express it as a weighted sum of many points around it. All points around it, actually, all the data points. Any point is a weighted sum of all the points around it. So y at a point I is equal to W1 Y1 plus W2 Y2 plus W3 Y3 plus W4 Y4. I just need a way to figure out what are those W's. By intuition wise, closer points get a higher W and farther away point get a lower W. That's what we will do after the break. Any questions? No. Again, you know, just take the math as entertainment value, nothing more than that. Other than that, you know, the concept is what you just need to know. There's a maximum likelihood. I start with a hypothesis, I build a likelihood estimator for that, and I use gradient descent in any of the global models. Okay. Other than that, nothing to really worry about. You know, everything is coded. Yes.
So just one last question. So in case of like FEM model, just like talked about, with FEM, every next value is a function of a previous value, right?
No.
In a way, not
Right,
not
right.
exactly. Like suppose you're talking about say temperature. I mean, we have a rod and we.
Oh, okay. There are two things here. I misunderstood your question. So if I have a rod, is this a function of the temperature here?
Yeah.
Yes, it is.
I mean,
I thought when you said, but they are not that worried about it. If I know the temperatures at 4 points, there is a nice way to predict what happens in between. What on the other hand they are interested in is, I have a rod, I am interested only on 1 point. Now, what material, what fluid strength, with what velocity if I send water, the temperature here will be will always be less than 25. So they are not interested in if temperature here is 25, what is the temperature here is another problem, solvable. When I am designing a car, what I am interested in is I have this pipe. If I do it with some kind of steel, the temperature is at 30. Another kind of steel, the temperature is 28 with the same fluid flow. What flow I should do, what should be these external parameters to ensure that this is less than 25. Instead of building that rod manually, they model it, simulate it with various possible material properties and various possible fluid flow properties.
But suppose the relation between these two things is of sinusoidal nature, or suppose
typically it's a partial differential equation that is very difficult to solve. It's not simple sinusoidal.
So, basically what we're trying to do with RBF is we're trying to fit in our sinusoidal sum of terms.
Exactly.
So it may not actually cover what actually.
Yes, you're absolutely. So that's why the best I'm saying is, given I see a Y like this, what is the most approximate function that I can build that has the desired properties?
So first I'll try with exponential sums, then I'll try with.
First, actually, you should try with linear. If it's line, it has 10% error. Then I'll go with exponentials. And then I'll go with even exponential to the power of exponential. That's what neural net does. Every layer I add, it adds an exponential in the base. And then at some point you have to settle down. The only checkpoint for you is what is the error on the test data. If your approximation is truly nice, the point that you know is on the training and test you should have very similar error. That's the best guess you can make. How else you know? Can you think of any other way in which you know your approximation is right or wrong? That's why we developed this elaborate way. There is a training data, testing data, evaluation data. I approximate based on my training and then test it on testing, and then finally I report my evaluation because of this thing only. Maybe I am more fitting. I am taking as much care as I can. And then the other thing, I regularize. I can build a complex model with high accuracy, less complex model with slightly lower accuracy. I minimize that. So you build regularization. You do everything to ensure, particularly, remember this guys, it is easy to move with all these tools from linear to nonlinear now. You can move. The moment you get into nonlinearity is where you need to worry about overfitting. Linear regression, you can't go wrong most of the times. You will get it all, you will not overfit it. But if you are now venturing into a radial basis or a kernel regression, be doubly and triply ensure that you are checking for overfitting. So do your evaluation data sets, try to regularize as much. When you have many columns, or when you are trying a very highly nonlinear model, is when you have to be ultra careful about overfitting. Because all you are doing is to take the best guess of the function that connects y and x. It's only a guess.
But then when you explain it to a client, suppose who is working in this industry, that everybody knows that since it's a differential equation, they may be expecting an answer that
but in a retail case,
would come in some this program. But if you show that it's a linear.
So again, that's a classic conflict, right? Do you want is this problem accuracy driven or explicability driven? If all you need is accuracy, and if you think a nonlinear approximation is definitely giving a worthier accuracy, then you apply it. But on the other hand, if it's explicability, you restrict yourself to linear regression and focus more on identifying newer attributes and even better attributes, and then do it. Okay.
Yeah,